So I've had this crazy idea in my head for a little while to make a 3D printed pressure vessel. Now let me start off by saying that this is probably a bad idea, especially if you were to use a 3D printed air tank for a pneumatic system. There's a lot of energy that can be released when something goes wrong in a pneumatic system, so I wouldn't recommend trying this, but I have seen at least one other YouTube video of somebody doing something similar. And I thought I would try to take this idea to the max. So anyway, the premise behind this was to try a couple different materials with a couple different print settings and attempt to make a 3D printed pressure tank. And then I'd throw this pressure tank onto a fixture that is meant to break things like this by injecting very high pressures into them. So the pressure tank that I designed in question is a 3-inch long tank, 2 inches in diameter, kind of vaguely modeled off of like the large propane tanks that you'd see outside of a house. The bottom of this tank has a 1/4 inch NPT thread in it. That way I can just screw this onto a standard fitting and do pressure tests with it. The thickness of the tank was governed by the number of walls that I tried to print. So I did 2 sets of these. I did one with 4 walls and one with 6 walls, and I changed the CAD model so that the wall thickness was correct for the number of walls that I had set in the slicer. They were all set to 100% infill, but most of the parts on this really wouldn't be using much infill anyway, so that probably didn't make a huge difference. And I printed a total of 4 test models, 2 in PLA, 2 in PETG. So I tested these using high pressure water, which is about the safest way that you can do this because high pressure air has a lot of issues. If you get something that goes wrong, it explodes. What happens is you send pieces of shrapnel everywhere. Since water is incompressible, you don't really have to worry about the energy that could potentially be stored up behind it. It's gonna get a little bit of a pop when it first goes, but after that your energy is pretty much gone. And this of course was done in an enclosure, so if a piece of shrapnel did go flying, it wouldn't hit anybody. Now the test fixture that was used here is capable of up to about 2,000 PSI, I believe, which is way more than what we hit, but we also hit much higher pressures than what I was expecting as well. So I printed these on my Prusa i3 Mark III's and pretty much with the default 0.2 millimeter settings, other than the fact that I changed the infill to 100%, and on some of them I changed the default number of walls from 2 up to 3, and you get, the way that I had it set up, you had 2 walls on the inner perimeter and 2 walls on the outer perimeter, so it's a total of 4 or 6 walls. So using Hatchbox PLA with 4 walls, the test piece maxed out at 279 PSI before it cracked and let all the water out. With 6 walls, this number was raised all the way up to 495 PSI, so almost 500 PSI of water pressure being held in a small 3D printed part, which I thought was pretty incredible. But moving on to PETG with 4 walls, that got up to 336 PSI, which is a pretty good jump over the 279 that we got on 4 walls of PLA. And unfortunately, the 6-wall PETG print did not hold enough water to actually build pressure. It was leaking so much that it would not get past 476 PSI was the max that I got out of it. So our highest pressure test was 495 PSI held in a cheap 3D printed plastic part. Now, as I said, all of these were leaking, so technically none of them held any pressure whatsoever, but they were leaking slow enough that I could still ramp the pressure up and get them to burst. The other thing that was really interesting to me about this is I was fully expecting these parts to break along the layer lines and just have a nice clean break across the surface. And they don't. They actually kind of shatter and spiderweb when they go. So I think that's a good indication of having strong layer adhesion, but not really the result that I was expecting. The other flaw on this test is that you really should have a bigger sample size. At least 3 or 5 of them would be better. I only did 1 test of each part, just as a proof of concept. And honestly, I was not expecting them to hold as much pressure as they did, and I was really impressed by these results. The other thing that I found surprising was that the threads actually held up really well. I was kind of worried about the parts ripping out of the thread when it started getting pressure, but nope, the tank itself failed. The threads held up great, and really, as a test part, it worked pretty well. I'm not sure that this information is really super useful for anything. I'm not sure that there's too many people that are wanting to use 3D printed pressure tanks. The one thing that originally made me start thinking about this was 3D printing tanks to run pneumatics on like competition robots. Now, I'm not entirely sure that this would be allowed by competition rules, but it was kind of an interesting thought to me to be able to make custom-sized tanks and potentially custom shapes to fit into spaces of your robot a little bit better. Though, as I said, doing this with pneumatics is quite a bit more dangerous than doing it with water like I did in this test in case something does go wrong. But from what we've learned here, doing a tank, at least in the way that I've designed it here, with 6 walls of PLA, you get 495 PSI. So even with a nearly 5x safety factor, you could run this at 100 PSI and feel reasonably confident that they're not going to explode. Granted, I still don't recommend using these as air tanks, though in theory, it could be possible if you could make one airtight. Now, in order to make these air or watertight, I think the easiest way to do it, or the easiest thing to try, would be to bump up your extrusion multiplier some. I think the default is probably 0.98 or 1 in Prusa Slicer for the filament that I used and everything else. But you could go up to 1.02 or 1.05. What that'll do for you is just give a little bit more plastic and it'll fill in the gaps in the extrusions. That way, hopefully, you don't have any pinhole leaks like I did. But to me, this mostly just gives you a good idea of how strong a 3D printed part can be, because this is kind of crazy to me. I didn't think they would get anywhere near this high. I was expecting maybe 100 or 200 PSI, nowhere near 500, potentially even more than 500 on the 6-wall PETG print. That one, unfortunately, we couldn't get to build pressure because it was leaking too much. But anyway, I thought it was an interesting result, and I figured I'd share it with the world just to sort of show off how strong 3D printing can be. So that's it for this video, guys. It was a pretty short and simple one, but I'll see you in the next one. Bye.